All right, here we go. So we're going to learn today about conservation of momentum. All right, most of this is going to be a review from stuff we learned last year. All right, so really quickly, law of conservation of momentum says the total momentum of a closed system will always remain constant. So remember, a system is just a collection of objects in a problem, whether it's two carts that are bumping into each other, or a bullet and a block of wood that the bullet is going to hit, whatever. All right. Now, a closed system is a system with no external forces. Okay. So what that means is the net force on our system is going to be zero, right? So what do we mean by external forces? Well, remember that just means a force that is applied by an object that is not in the system. Okay. So there are a couple of ways of thinking about this. In terms of the third law, it's this. So suppose I've got a system that consists of objects 1, 2, and 3. Okay. Well, that means that the velocity of the center of mass of that is going to be the mass of object 1 times the velocity of object 1 plus the mass of object 2 times the velocity of object 2 plus the mass of object 3 times the velocity of object 3. Well, notice that's just the momentum of object 1 plus the momentum of object 2 plus the momentum of object 3, right? So to find the velocity of the center of mass, you just divide by the combined masses, which isn't going to change at all, right? Okay, and so the idea is, as long as our net force is zero, that means this velocity stays constant, which is a fancy way of saying that this total momentum is going to stay constant. Okay, because your mass clearly won't change. All right, so that is that. All right, and then the third law explanation I'll give in a minute. Okay, but that's basically an explanation based on, really, I guess it's Newton's first law, right? Because they're saying your velocity is constant because your net force is zero. Anyway, so let's do an example. All right, so there are kind of two ways of solving these closed system problems. All right, these conservation of momentum problems. The first way is to do it using total momentum. All right, so here's the way that's going to look. You're going to say, all right, so again, suppose your system consists of objects 1, 2, and 3. All right, so what you're going to do is you're going to say the total momentum that objects 1, 2, and 3 have before the collision is equal to the total momentum that objects 1, 2, and 3 have after the interaction, I guess I should say. It might not be a collision. It might be that the objects are pushing off each other or whatever. All right. So what does this mean? Well, total momentum before the collision. That means the mass of object 1 times the velocity of object 1 before the interaction, plus the mass of object 2 times the velocity of object 2 before the interaction, plus the mass of object 3 times the velocity of object 3 before the interaction. So that's my total momentum before the collision. And then the total momentum after, I keep saying collision, I'm sorry, it's habit. It doesn't have to be a collision. It could be objects pushing each other or running into each other or interacting in any way where they're pushing each other, okay? Or pulling each other for that matter, okay? So here's our total momentum before the interaction, all right? Total momentum after the interaction is this, mass of object 1 times the velocity of object 1 after the interaction, mass of 2, velocity of 2 after the interaction, mass of 3, velocity of 3 after the interaction. Okay, and obviously if we had 4 objects, you'd add on a 4th object. All right, so this is kind of the jam. This is the equation we kept using in honors to solve these problems. Usually we just had 2 objects, but whatever, it works for any number of objects. All right, so let's solve the problem using this so you can see how this works. All right, so here we've got a 1,250 kilogram truck rolling at 5 meters a second, and then it's going to collide, i.e. interact, head-on with a 750 kilogram car going at 8 meters a second. If the vehicles stick together during the collision, find the final velocity of the 2 vehicles and determine how much kinetic energy was lost. All right, so here we go. I always like to make a drawing. So here's my truck. Mass of truck is 1,250 kilograms. Here's my car. Mass of car is 750 kilograms. All right, let's see. The velocity of the truck initially is 5 meters a second. The velocity of the car initially is negative 8 meters per second. Please watch your signs. All right, and then after the collision, I don't know the velocities. So there's some velocity for the truck final, and there's some velocity for the car final. But I know those are equal to each other, right? Because they are stuck together. So let's call the two final velocities VF. Okay? And so now all we're going to do is we're going to solve this. And we're going to solve it by using that equation that I just had on the board. We're going to say that the total momentum before the cars collide is equal to the total momentum after the cars collide. So that means the momentum of the car, that means the momentum of the truck before the collision plus the momentum of the car before the collision has got to equal the momentum of the truck after the collision plus the momentum of the car after the collision. So let's plug in our numbers. Oh, we can't plug in numbers yet. So this is mass of truck, velocity of truck initial, plus mass of car, velocity of car initial, equals mass of truck, velocity of truck final, plus mass of car, velocity of car final. Now I'm just going to plug in my numbers. So I get 1250 kilograms times 5 meters a second plus 750 kilograms times -8 meters a second equals the mass of the truck is 1250 kilograms. Oops. Times VF plus the mass of the truck, or the mass of the car, sorry, 750 kilograms, also times VF. Okay, so the left side of this equation is the total momentum before the collision, right-hand side is the total momentum after the collision. So add these up. So this number here on the left gives us 6250 minus 6,000. These are kilogram meters per second. Equals 1250 VF plus 750 VF is just 2000 VF. So now I'm looking at 250 kilogram meters a second equals 2000 VF. Divide both sides and your VF turns out to be 0.125 meters per second. Okay, so there we go. All right, that's a conservation of momentum problem, right? And we used it by saying that our total momentum stayed constant. All right, now, the question also asked us to find out how much kinetic energy was lost. Okay, so let's do this. Let's figure out what was the total kinetic energy before the collision. Oh, well, that would be the kinetic energy of the truck before the collision plus the kinetic energy of the car before the collision. So that's 1/2 times the mass of the truck times the velocity of the truck. Don't forget to square it. Plus 1/2 mass of the car times the velocity of the car. Notice the negative doesn't matter because it's going to square out. I'll just add it. You guys can chug this into your calculator. You get 39,625 joules. All right. Now, if we repeat that process, but replace both of these initial velocities with our VF of 0.125 joules, then you find that your total kinetic energy after the collision is a meter 15.6 joules. All right, so I'm going to talk about this a little bit more in the next video, but to shorten up the next video, I wanted to do it here. This collision here is what's called perfectly inelastic, and you'll get this definition again in the next video. But it's called perfectly inelastic, and that is the name of a collision. Perfectly inelastic. That's the name of a collision where your objects stick together. And you'll notice in this collision, we lost a ton of kinetic energy, right? And that is one of the defining properties of a perfectly inelastic collision, is it maximizes, it's the most energy you could possibly lose so that you still conserve your momentum, so your total momentum does not change. All right, so that is one type of problem. Notice we solved that by saying that our total momentum did not change. All right, now there is another way we can get about solving these problems. All right, and the other way to do it is by looking at the change in momentum. All right, so check it out. Here's what we just did in the video. So we looked at the total momentum before the collision and the total momentum after the collision. And what we said was that the momentum of the car before the collision plus the momentum of the truck before collision has got to equal the momentum of the car after the collision plus the momentum of the truck after the collision, right? Now, if we rearrange these a little bit, here's what I'm going to do. Let's get all the car stuff on one side and all the truck stuff on the other, okay? Let's subtract PTI from both sides. And let's subtract PCF from both sides. Okay, if we do that, on this side, you get the momentum of the car initially minus the momentum of the car final. And on the other side, right, because these guys cancel out, on the other side, you get the momentum of the truck final minus the momentum of the truck initially. Okay, well, what is that? Well, this momentum of the truck final minus the momentum of the truck initially, that's the change in momentum for the truck, right? And on the other side, that's the change in momentum for the car, but it's flip-flopped. So it's the opposite of the change in momentum for the car, right? So what this is telling us is that whatever momentum is lost by one object must be gained by the other, all right? And this is a result of Newton's third law. Check it out. Here's my truck. Here's my car, right? During the collision, they're both going to exert forces on each other. Here's the force of the truck pushing the car. Here's the force of the car pushing the truck. Change in momentum is net force times time, right? Assuming your force is constant. Well, because there are no external forces in the system, the net force on the car is the force of the truck, and the net force on the truck is the force of the car. Those are equal and opposite, right? So these two forces are equal and opposite. They act on each other for the same amount of time, so your change in momentum is equal and opposite. All right, and the same logic works if your force is not constant, because then you just get the integral of your net force with respect to time. So you're going to integrate over the same time interval, and your forces are equal and opposite. All right, so long story short, you can solve conservation momentum problems by, instead of considering the total before and the total after, you can say that whatever is lost by one object must be gained by the other. All right, let me show you how that works. So honestly, I'll be honest, I almost never do this. Really, the only time that I do this is, and this is worth writing down, if you have an unknown mass. If you have an unknown mass and you're trying to find that mass, this is the jam. It makes things a little bit easier, all right? So let's do an example, and then we're all done. Look at us go. All right, so here we go. We got balls A and B. Let's embiggen the screen a little bit. Balls A and B are traveling toward each other at a speed of v. Okay, so here we go. Here's ball A. Here's ball B. Let's see. We don't know any of their masses. In fact, we're trying to find the ratio. So let's call this mass A. Let's call this mass B. The velocity of A initially is v. The velocity of B initially is negative v, right? Because it's going in the other direction. Then it says after the collision, A is still moving forward at a speed of v over 2, and ball B is bounced back. But backwards for B is going to be this way. So the velocity of B final is 2v. Okay, and we're trying to find the ratio between their velocities. All right, so let's do this. So let's move my drawing over, clear up some space. So here we go. So the idea is the change in momentum for ball A is equal but opposite the change in momentum for ball B. Whatever's lost by ball A is going to be gained by B. Notice it doesn't matter where you put the negative sign. You've got to have a negative on one side, right? Okay, so change in momentum for A. Well, that's the mass of A times the velocity of A final minus the velocity of A initial. That's got to equal the mass of B times the velocity of B final minus the velocity of B initial. And don't forget that negative sign like I just did, so we're going to tack in a negative sign in there. All right, so now let's plug in our numbers. Let's see, mass of A times, let's see, the velocity of A final is V over 2 minus the velocity of A initial is V equals negative mass of B times the velocity of B final is 2V minus the velocity of B initial is negative V. So let's simplify. So this is mass of A times V over 2 minus V. So that's half of V minus V. So that just gives you negative v over 2 equals negative mass of v times, let's see, 2v minus negative v is 3v. All right, so let's see. So what cancels here? So first of all, if I divide both sides by v, the v's all cancel. I can multiply both sides by -1 to get rid of my negatives, and then multiply by 2 to get that the mass of A is the mass of B times 6, which means then that our ratio is 6. All right? Okay, so the reason that I said that at the beginning, I said usually I use this method if you don't know a mass, is because if you do it this way, it puts your unknown mass so that everything related to that unknown mass is on one side, right? Whereas, let's go back. Suppose we hadn't known the mass of the truck or the car in that previous problem. If you don't know the mass of the truck or the car, then you have an unknown mass here and an unknown mass here, right? So that gets ugly. All right? So 9 times out of 10, I think you're going to find that you use this equation. But I do think the other one is a valuable problem-solving tool. All right? So there we go. That is it for that one.